Good morning, Mr. Lee and other senior management team of Value Price Supermarket, Dr. Jawad, Kok Yong, fellow classmates and guests. My name is Yeong-nam, a business data analyst with Success Consultancy. Thank you for giving me this opportunity today to present to you the findings of the feasibility study commissioned by Value Price on transforming tomorrow's supermarket today by leveraging technology to do more with less. Let me begin with a quick introduction of myself. Everyone has those moments in life when the decisions they make are pivotal, not just to themselves, but also to those around them. My career mission statement is to help people be the best in the moments that matter. I began my career 29 years ago, the first 11 years with a strong technical foundation as a satellite RF engineer and later as a network architect for mobile cellular communication. Building on top of that, I took on key roles in pre-sales, bid and quote commercial management, looking after pricing, tender proposals, then in product marketing, and for the last 11 years as head of product operations for the entire APAC region. In this last role, which I helmed for 11 years, my responsibilities ran the gamut from product auditability, pricing, training, quality, demand planning, product roadmap prioritization to P&L analysis, and business development, such as opening of new vertical markets. So my technical and business background put me in a strong position in my current role as a business data analyst, as I understand how to bridge business requirements with technical challenges. Let's now look at the business problem that we face today. Today, there are 632 supermarkets in Singapore. The business model for successful supermarket operations is as follows. Attract as many customers as you can. Make them stay as long as you can, and they'll buy as much as they can. Now, to achieve the above, a supermarket has to embrace the 3 V's. First, variety. Stock as much variety as possible to cater to different needs. Volume. Move as much volume as possible to lower your costs. And number 3, versatility. Adapt as much as possible as consumer preferences change, which happen frequently. Next, let's look at the business landscape. The supermarket business in Singapore is a lucrative business. Here's what statistics tell us. An average household in Singapore spends about $350 to $475 a month on groceries. 80% of them do their purchases on site, with online shopping starting to take off as well. There are 1.3 million households in Singapore, and that means the TAM, the total available market, is a whopping $500 million a month and growing. In fact, the market grows at an annual rate of 14.5% and is expected to reach 9.9 billion by 2023, which is next year. Now, but while the business is growing, cost is also growing. The 2 biggest costs to supermarket operations are manpower and rental. Manpower costs make up 42% of total OPEX, and rental take up the remaining 36%. Now, this situation is going to get worse with government policy to tighten the ratio of foreign workers and the higher cost of employing locals. For your information, locals cost 20% more. This is the conclusion from the survey done by DBS Bank. Companies would therefore need to invest in technology in order to do more with less and to lessen dependence on manpower and enhance the shopping experience. What is the solution? The proposed solution is MATE, which stands for Marketing Anti-Interactive Dashboard. What is MATE? MATE is an end-to-end solution that harnesses the best of online shopping with the best of on-site experience. Online shopping provides information at your fingertips and ease of payment, whereas on-site allows shoppers to feel and touch the products, an important approach to form connection. Here's how MATE works at a high level. A shopper enters a store. He opens his MATE app on his phone and points his camera at a product that he's interested in. The image is sent automatically to the cloud where it is correctly classified. The cloud then intelligently pushes information to the shopper. Basic information such as pricing, country of origin, is there any sales offer going on, and also customized, personalized information. For example, the recipe for dinner tonight and other recommendations. Now, indirectly, by knowing what the shopper is pointing and classifying at the products, we are actually knowing where the shopper is in the store, and therefore the store can track the location of the shopper and what he's interested in and what he spends his most time on. Once the shopper is happy, he adds the item into cart and continues shopping. MATE will continue to monitor his progress inside the store, and based on his information and those in his cart, push further personalized information to him. So this is like shopping with a service staff by his side. Once the shopper is satisfied, the shopper pays for his items online. There's no need for a checkout counter or even dedicated cashiers. At the exit, the shoppers pack the items and the staff verify the physical items tally with the cart. Therefore, checkout time is cut. And there's also potential for real estate savings, which can be used to stock products instead. Key to the success of MATE is the correct image classification, which is the focus of this capstone project. It has to be right. First time, every time. For this feasibility study, we have two objectives. Build an image classification machine learning model for 3 categories of products with an accuracy of at least 90%. The categories that were chosen are fruits, packages, and vegetables. Number 2, recommend suitable machine learning models to use for actual production. Let's move on to the dataset. The dataset used for this image classification model for 3 is taken from Kaggle with 5,122 images that are split into 3 categories. We have deployed online augmentation to increase the size of the dataset and also as a form of regularization. 4 models were used in the analysis. One is a base CNN model that we try to configure ourselves. The other 3 are pre-trained models, VGG16, Inception V3, and MobileNet V2. The images are sized 224 by 224. Note that there are sub and sub-sub categories of fruits and packages and vegetables which can be considered for future work. In total, in this dataset, there are 77 sub-sub categories in this dataset. Let's now look at the analysis of our findings. But before that, a quick look at the samples of what we pull out from the dataset, the images, and also what are some of the images for image augmentation. From the learning curve, we can see that all 4 models perform reasonably well. Based on the metrics of at least 90% accuracy, VGG16, Inception, and MobileNet make the cut, with further work needed on the base model. So we can see that in summary, the mobile net performed the best so far, followed by Inception. Pre-trained models in general seem to perform better and faster in terms of accuracy. So this is our findings. Our pre-trained models seem to be doing better, and therefore we should consider and recommend to use pre-trained models for a start in actual production. What are the next steps? One of the things that needs to be done is to increase the breadth and depth of classification. The breadth is to cover more variety of products and producers, and the depth is to extract more insight. For example, is an apple ripe or unripe? Is it good? Is it bad? And finally, we mentioned before that image classification is the first important key step in the whole end-to-end process under MADE. The actual deployment will have to be done in the cloud using agile process and for end-to-end testing to take place. And these are the references that have been used for this study. So in summary, Mr. Lee and other senior management team of Value Price Supermarket, Dr. Jawad, Kok Yong, fellow classmates, and guests, this is what MADE is all about, transforming tomorrow's supermarket today. Thank you. Next, I'll go on to share the notebook. I've used Kaggle notebook, and this is, I started off with an overview, the objectives, and went on to the table of contents. I've stepped through them using numbering. So step 1, to check the software versions. Step 2, import the libraries. Step 3, generate the data sets. We have 3.2, we generate the data set for training using, and then generate the data set for validation, 3.3, and generate and also review the data set details. We've used image augmentation to increase the number of images as the data set is not big enough. Step 4 is to visualize the data in the data set. These are a quick random review of some of the images to see what we are looking at, what images we have. And we've also used further image augmentation to introduce image diversity by adding random and realistic transformation on the training set. And this is how the image augmentation will look like, the original image and also the augmented images. Step 6, we have built the models using the base CNN model and other models for transfer learning, VGG16, Inception, and MobileNet. We define the augmentation layer. We use the base CNN model. And then this is a summary. We've done the same 6.2 for VGG16 and do the same for 6.3, Inception version 3, and do the same for 6.4 MobileNet v2. After we have also included 2 other pre-trained model, ResNet 50 and EfficientNet for future work, so that we can increase our choices of pre-trained models. Step number 7 is to train the models. 7.1, we train using the base model with 50 epochs. Next, we move on 7.2. We use the same training, but now with VGG16. And again, 50 epochs so that we can see the curve. 7.3, using Inception V3, and the same for 7.4 using mobile net. Step number 8, we'll output the results of the models, put it into a data frame. Accuracy is a metric, but in order to make sure that we don't miss out anything, we've included precision and recall. Recall, make sure that we capture as much of the positive as possible, and precision tell us how much of what we have captured is being classified correctly. So these are additional parameters that we have used to double check on the nature of our metric. This is for base model 8.1, and in next 8.2, we've done the same for VGG 16, and 8.3 for Inception, 8.4 for mobile net, and step number 9 is to display the results of the learning curve. This is what we see. On the left side here is for base model, on the right side is a VGG 16. This is a loss curve, and this is the accuracy curve. The same for Inception, and also for mobile net. You can see the very nice curve for these two. Step number 10. After we have trained the models, we need to evaluate the models. And for that, we use a test data set, which is unseen data. So we evaluate the model for base 10.1. The accuracy is not fantastic at 74. And then 10.2, VG 16 is much better at 89, almost 90%. 10.3 Inception, we get 95. 10.4 mobile net, we get 96. And putting these all together, this is a data frame that we have put together to summarize the results. And 10.8, we do a simple test. We pick a random fruit. This is a fruit, and we predict it using a mobile net, and this is what we get. Okay, we have also deployed them on Streamlit. And this is the image from Streamlit. Okay, the categories are fruit, package, and vegetables. We pick a product. Oops, there it is. This is a package. We'll try the same thing again. Let's try a fruit. This is a fruit. And one last one. This is a fruit. He loves his apple. Thank you so much, everyone. Thank you for your time. This is the end of my presentation.